Good afternoon, everyone. Myself, Dr.M, working as Associate Professor at Geopolary Engineering College, Kurnool. Now, I'm going to explain you about digital signal processing subject. As you are aware, digital signal processing deals with the representation and transformation of the signals and the information they contain. If you take any subject, there are some prerequisites for the subject. Like DSP, you have the prerequisites. The basic subjects are signals and systems and analog communication, etc. The most prerequisite subject for this is signals and systems. I advise all of you to be thorough with this concepts of signals and systems. And we are going to stress more on discrete time signals rather than continuous time signals. As all of you know, signal is any function that represents some information. Broadly, we have studied about continuous time signals and discrete time signals in your signals and systems topic. We focus our attention more on discrete time signals here because DSP deals with discrete time signals rather than continuous time signals. Continuous time signals are defined over continuously a long time. They vary continuously a long time, infinitely a long time. Here both time and amplitude are continuous. When you take discrete time signals are obtained from continuous time signals by the method of sampling. Sampling is a process of converting the continuous time signals into discrete time signals. Of course, we have studied the rules for sampling also. Sampling is governed by a sampling theorem, which states that a strictly bandlimited signal of finite energy can be completely reconstructed from its samples if it is sampled at a rate greater than or equal to twice the maximum frequency. Fs must be greater than or equal to 2fm, where Fs is a sampling rate, Fm is the maximum signal frequency component that is present in signal. So there are two cases of sampling, that is Fs greater than 2fm and Fs is equal to 2fm. Fs is greater than 2fm, you get the spectra. The spectra have some gaps between each other. When you take this particular this one, the spectra for Fs greater than 2fm, the spectra will have certain sort of gaps here. If you assume the triangular spectrum, so this is for the case Fs greater than 2fm, and whenever Fs is equal to 2fm, the spectra will get perfectly aligned like this. This is the case for Fs is equal to 2fm. So for combinedly for both the cases, we are going to call the sampling as Fs greater than or equal to 2fm. In both the cases, sampling of the signal is possible. The sampling rate is less than 2fm, then the signal gets aliased. You cannot sample the continuous time signal, because whenever Fs is less than 2fm, you have the spectra which is getting overlapped. So the overlapped signal is lost here. The identity of the original signal is lost, and you cannot reconstruct the original signal from the sampled version, that is Fs less than 2fm. So this case is avoided. We are always going to take the case of Fs greater than 2fm and Fs is equal to 2fm. So this is called as oversampling case. This is called as perfect sampling case. And this last case is called as undersampling case. Undersampling is a sampling where you cannot reconstruct the signal from the original version. In all practical scenarios, we are going to prefer this situation Fs greater than 2fm, because sometimes it is not perfectly possible to have the condition Fs is equal to 2fm. This is about sampling, of course. So the process of converting continuous time signal into discrete time signals is called as sampling. Sampling is an important process because when you convert into discrete time signals, continuous time signals are represented continuously along time, whereas discrete time signals, they are defined at discrete instance of time. So when you take this particular continuous time signal, it is defined like this. So this continuous time signal, whenever you sample the signal is defined like this. The signal is sampled at discrete instance of time. Of course, you have studied some methods of sampling also in your lower classes, that is signals and systems. So a discrete time signal is readily accepted by a digital signal processor rather than a continuous time signal. A discrete time signal is readily accepted by a DSP processor rather than discrete time signals, rather than continuous time signals. So DSP subject deals with representation and transformation of the signals. Representation is important and transformation is important. Transformation of the signals and the information they contain. Transformation of what? Transformation of discrete time signals. We focus our attention more on discrete time signals here. Representation and transformation of discrete time signals. Representation means you can represent any signal in the time domain and frequency domain. Transformation, you can transform from time to frequency or frequency to time. You can transform from time to frequency or frequency to time. Of course, we are going to deal with the time to frequency transformations and frequency to time transformations also in our in this first unit of DSP. So DSP deals, digital signal processing deals with representation and the transformation of the signals, particularly discrete time signals, and the information they contain. Now let us see some of the advantages and applications of the DSP. When you come to the advantages, you can list out some advantages of DSP. The advantages of DSP are flexibility, ease of data storage, ease of data can be stored easily in this particular DSP system. Flexibility. DSP systems are more flexible compared to the analog systems. Implementation of sophisticated algorithms. Sophisticated means highly developed. Implementation of sophisticated algorithms. Of course, they are with high speed, economical, meaning to say the DSP processors are more economical compared to other processors. Accurate, reliability is important. They are more accurate. DSP systems are more accurate and they are reliable also. And when you come to the applications of this particular DSP, applications, they applied in various fields like consumer electronics, wireless communications, image processing, speech processing, military, radar, speech processing. Like there are many fields, innumerable fields that DSP is applied. This is only some of the fields, important fields I'm telling you. Digital signal processing is wide and variable fields. Okay, right. So this is about the introduction to digital signal processing and advantages and applications of this DSP. So let us now develop the basic block diagram of DSP system. Let us take into account the basic block diagram of DSP system. When you take the basic block diagram of DSP system, it has certain important blocks. What are the important blocks that are present in it? I've got first anti-aliasing filter. I've got a sampler. A to D converter. DSP processor. D to A converter. And reconstruction filter. Of course, you have got here, you are giving the input signal here, and you are generating the output signal here. This is the basic block diagram of DSP system. The important blocks are anti-aliasing filter, sampler, A to D converter, DSP processor, D to A converter, reconstruction filter on the output. The first block that is present is anti-aliasing filter. In this anti-aliasing filter, what is done here? You are ensuring the condition here. The name itself indicates that it is anti-aliasing. That means you are avoiding the condition Fs less than 2fm. That means you are imposing the condition here Fs greater than or equal to 2fm. That means you are ensuring that the sample signal is greater than or equal to, sampling rate is greater than or equal to twice the maximum signal frequency component that is present. Fs greater than or equal to 2fm. After the signal is ensured with that particular after the continuous time signal is ensured with that particular condition, then you are going to pass through a sampler where you are converting this continuous time signal into a discrete time signal. That is, you are converting a set of continuous time signal into certain set of samples. So at the output of sampler, you will get a discrete time signal. From now onwards, we give the abbreviation for discrete time signal as DT signal. DT signal means you understand that it is the discrete time signal. The discrete time signal is now given to the A to D converter block, where this is digitized. The signal is digitized. You might have studied various analog to digital converters in your classes, in your previous classes. So A to D proper, it is converted to, it is digitized and then is passed to the DSP processor. This is the heart of this particular digital signal processing system. DSP processor is going to process the digital signals appropriately. After this DSP processor, then you are giving to the D to A converter. The function of this D to A converter is to convert from digital signals to the analog signals. And finally, you are giving to the reconstruction filter. This reconstruction filter is generally a low pass filter because finally require the low pass signal frequency components. This reconstruction filter is going to reconstruct the output from the analog signal. Finally, of course, the output that you are going to get is an analog signal only. So this is the basic block diagram of a DSP system comprising of anti-aliasing filters, samplers, A to D converters, DSP processors, D to A converters, reconstruction filter. Right. Now let us have the recap of the discrete time signals and systems. What are the basic discrete time signals and systems? First, let us take up classification of discrete time signals. Classification of discrete time signals. Of course, this difference between a signal and a system is, signal is any function that represents some information. A system is any physical entity that acts on the input signal to produce the output signal. That's a system. Of course, we define that system afterwards. We are going to give a quick recap of this particular classifications of discrete time signals and systems, because we'll be dealing with discrete time signals and systems throughout our DSP. So it is important to know about the classifications of discrete time signals and systems. First, let us take up the important classification of discrete time signals. The first and foremost classification under this is deterministic and random signals. Deterministic and random signals. Second classification is causal, anti-causal and non-causal signals. Causal, anti-causal and non-causal signals. The third classification is symmetric and anti-symmetric signals. The fourth classification is periodic and aperiodic signals. Of course, the last classification is energy and power signals. These are the classifications of discrete. Of course, a discrete time signal can be represented in different forms. All of you know about this particular representation of discrete time signals. Suppose x of n is any discrete time signal. It can be represented as, in the sequential representation, it can be represented like this. So when you give a 0th sample, it means that it is the first sample. Okay, this is called as a sequence representation. The sequence representation. How can you represent it graphically? Graphically, this can be represented like this. You plot n versus x of n. X-axis is n, y-axis is x of n. Of course, you are giving the discrete time values 0, 1, 2, 3. And what do these numbers inside this flower brackets represent? Inside the brackets represent. They represent the amplitudes generally. So you are going to plot the amplitudes at different time instants. 1, 2, 3, 4 like this. 1, 2, 3, 4 are the amplitudes of this particular discrete time signals. Of course, more prominently, it is a causal discrete time signal, meaning to say that it is a passive duration discrete time signal. This is called as a sequence representation, the above one. This is called as a graphical representation of the signal. Always we represent with the small arrowheads like this, meaning to say that they are sample values, amplitudes. This same signal can be represented in the functional representation. How can you represent the functional representation? So you can represent like this: x of n is equal to 1 for n is equal to 0, 2 for n is equal to 1, 3 for n is equal to 2, and 4 for n is equal to 3. It is defined like this. This is called as a functional representation of the signal. All of you should know these three forms of representation of the signal, because they are oftenly coming into picture. You should know the conversion also. Suppose a signal is given in sequence representation, you should be able to convert it into graphical representation. Suppose if the signal is given in functional representation, you should be able to convert it into the graphical. And if it is given in the graphical also, you should be able to convert it into other forms. Any form can be given, you should be able to convert into the other forms. So this is a causal signal. Cause assumes that it is a passive sided signal. Right. Now coming to the classification, of course, you have studied about, suppose I shift the arrow mark like this, x of n is equal to 1, 2, the same signal can be joined in this. It is a non-causal, becomes a non-causal signal. These are two-sided signal. We come to this in this particular causal, anti-causal and non-causal signal representation. First, let us talk about deterministic and random signals classification. A deterministic signal is said to be a deterministic signal if it's predicted by different mathematical rules and different mathematical equations. So its future values are predicted by the means of mathematical equations. If the future values are not predicted by the help of mathematical equations, it is called as a random signal. A deterministic signal is a one where the signal is predicted by different mathematical rules. All the signals that you have now, step signal, ramp signal, parabolic signal, impulse signal, they are all deterministic signals. Random signal is different. Random signal is not represented by the future values. The future values are not represented by different mathematical equations. So random signal best example is a noise signal. A noise signal is the best example of a random signal. Of course, one more example here is a ECG signal, because it is not defined by different time period and different frequency. The noise signal of this is not defined by different time period and frequency. So it's a random signal. The signals that you are all dealing with all are deterministic signals. This is about the first classification. Coming to the second classification now, causal, anti-causal and non-causal signals. First, let us define what is meant by a causal signal. Causal signal. Causal signal is one. So mathematically, how we define this particular causal signal? Here x of n is equal to 0 for n less than 0. That means x of n is going to exist only for n greater than or equal to 0. X of n is equal now, if x of n is 0 for n less than 0. Examples are, if you take a finite duration signal, x of n equal to, just now we have discussed that, 1, 2, 3, 4, with the 0th sample located at 1, is a finite duration causal signal. Similarly, u of n, r of n, etc. U of n, all of you know, it's a step signal, unit step signal varying like this. All of you have studied about the, so unit step signal has equal amplitudes defined like this. It is the best example of an infinite duration signal. How can I represent this with the help of sequence representation? Generally, u of n can be represented as 1, 1, 1, so on. There are infinite samples here. The first sample is located at this one. You can represent it functionally like this. U of n is equal to 1 for n greater than or equal to 0, 0 for n less than 0. This is how you can represent it as a functional representation. Next, when you take a ramp signal, how can you represent it functionally? R of n is equal to n for n greater than or equal to 0, 0 for n less than 0. You can represent this function, this graphically like this. So, of course, when you extract the samples here, r of 0 is equal to 0, r of 1 is equal to 1, r of 2 is equal to 2, and so on. So r of n is equal to n for n greater than or equal to 0, 0 for n less than 0. So these two are the best example of infinite duration causal signals. Infinite duration causal signal. This is a finite duration causal signal having finite number of samples. Of course, the 0th sample indicates the first position. This arrowhead indicates always the position of the 0th sample. So this is about the causal signal. When you take up the anti-causal signal, the second one, anti-causal signal. Here, x of n is equal to 0 for n greater than 0. So means that the anti-causal signal is a negative sided signal defined for only n less than or equal to 0. What are the best examples for this particular anti-causal signals? Examples are x of n, when you say x of n is equal to 1, 2, 3, 4 with a 0th sample located at 4 here, and one more example is u of minus n, r of minus n, etc. These are the best examples for an anti-causal signal. Of course, this is a finite duration anti-causal signal. These two are examples for infinite duration anti-causal signals. When you plot this particular anti-causal signals, the finite duration sample, n versus x of n. So it is defined as a negative range 0, -1, -2, -3, etc. And 1, 2, 3, and 4. These are the sample values for this particular signal. So negative sided, this is at located at n is equal to 0. This is located at n is equal to -1. This is at n is equal to -2, and this is at n is equal to -3. Right. So this is a negative sided signal. When you take up this u of minus n, how can you define this? How can you plot this particular signal? U of minus n indicates folded version of u of n. This is a folded version of unit step signal u of n. Folded means it is a time inverted version. Folded means it is a time inverted version. So if you plot it graphically, the signal looks like this, u of minus n. So amplitudes, there is no change in the amplitudes, but there is an inversion in the time. The signal vary, what are the limits of this u of minus n? It is going to vary from minus infinity to 0. It is going to vary from minus infinity to 0. U of n varies from 0 to infinity, whereas u of minus n varies from minus infinity to 0. The last sample here is 0. Similarly, r of minus n, that is the inverted version of ramp signal, looks like this. So n versus r of minus n. So this is 0, -1, -2, -3, etc. Okay. So all these are the examples for anti-causal signals. So an anti-causal signal can be finite duration or infinite duration. Right. Next, coming to the classification of a non-causal signal. A non-causal signal is otherwise called as a two-sided signal. A non-causal signal is a two-sided signal where x of n is not equal to 0 for given values of n. X of n is non-zero for given values of n. This is a non-causal signal. What are the best examples for these non-causal signals? X of n is equal to 1, 2, 3, 4, 5. Suppose the 0th sample is located like this. And if you take the infinite duration, u of n plus u of minus n, etc. These are the examples for this non-causal signal. So first signal is a finite duration. The second signal is infinite duration non-causal signal. So two-sided signal. Even if remember that even if one sample exists on the negative side also, it becomes a causal signal. For example, you have u of n plus 2, let us say. It is also a non-causal signal, infinite duration signal. So when you plot the first one, it looks like this. 0, 1, 2, etc. Negative side you have minus 1, minus 2. 1, 2, 3, 4 and 5 are the sample values. And when you plot the second signal, it's just the addition of the step signal u of n and the inverted version of the step signal. So when you add u of n and u of minus n, u of n is like this, u of minus n is like this. When you add up both the signals look like this. So 0, 1, 2, 3 on the positive side, minus 1, minus 2, minus 3 on the negative side. All are ones except at 0 you have amplitude of 2, because at 0 you have u of 0 plus u of 0, it is 1 plus 1, it is 2. So the amplitude of this one is 2. Whereas all this one is, it is this one. So it's a two-sided signal. Coming to the third one, that is the third signal, that is u of n plus 2. U of n plus 2 is what? U of n plus 2 is left shifted version of u of n by 2 units. Left shifted version of u of n by 2 units. So u of n is a causal infinite duration signal. So when you left shift it, it looks like this. So we have got two samples on the negative side, like this. Of course, on the positive side you get an infinite duration signal. Negative side, the signal is extending only up to n is equal to minus 2. The signal is starting from n is equal to minus 2 to plus infinity. This is the range of the signal. The signal is defining from n is equal to minus 2 to plus infinity. This is the range of the signal. So here I am observing that only two samples are existing on the negative side. So even if this is a non-causal signal, whereas infinite samples are existing on the positive side, whereas only two samples are existing on the negative side, even then it is a non-causal signal. Like for example, you have, if we take a finite duration case, x of n is equal to 1, 2, 3, 4, etc. with the arrowhead located at 2 here. And one more example is x of n is equal to 1, 2, 3, 4 with the arrowhead located at n is equal to this one. So here what you are observing, one sample is located at negative side here, and this one sample is located on the positive side. Even then it is a non-causal. It is not an anti-causal signal, but it is a non-causal signal. So x of n is non-zero for given values of n. This is a non-causal signal. Anti-causal signal is purely a negative sided signal where you get only the negative values, negative sided values. So these are about the second classification of discrete time signals, that is the causal, anti-causal and non-causal signals. Now coming to the important properties of important properties of discrete time signals. What are the different operations? What are the important operations that can be performed on discrete time signals? All of you have studied this in signals and systems. These are very important properties that have to be studied. Suppose x of n is any discrete time signal, then x of n minus k represents the right shifted version of x of n, right shifted version of x of n by k units. X of n plus k represents left shifted version of x of n by k units. So the first operation is also called as delayed version. The first operation is also called as delayed version. The second operation is always also called as advanced version. The signal is advanced in time. Remember that n always represents time in the case of discrete time signals, whereas t represents time in the case of continuous time signals, n represents time in the case of discrete time signals. Then x of minus n denotes time inverted version of x of n. It is also called as time reversed or folded version. It is also called as time reversed or folded version. Then x of k minus n is nothing but, it is also called as, it is also can be represented as x of minus k plus n. So it is inverted and right shifted by k units. Inverted and right shifted by k units. Of course, the next classification is x of minus k minus n or x of minus n minus k. This is the inverted first and left shifted by k units. All these are the different operations that can be performed on signals, discrete time signals. First of all, it is x of n minus k, right shifted version of x of n, called as delayed version. X of n plus k, left shifted version of x of n by k units. And x of minus n is time inverted version of x of n, time reversed or folded version. X of k minus n or x of minus n plus k is inverted and right shifted by k units. Finally is x of minus k minus n or x of minus n minus k. It is the inverted and left shifted by k units. So let us take an example here and then discuss about these properties. Let us take that x of n is equal to some 1, 2, 3, 4, 5. And you are going to perform all these operations on the signals. Perform. First operation is x of n minus 2. Second operation is x of n plus 2. Third operation is x of minus n. Fourth operation is x of 2 minus n. Fifth operation is x of minus 2 minus n. Perform these operations on this particular signal. So by seeing itself, you can tell that the first operation is the right shifted version, that is the delayed version. Second operation is the left shifted version, that is x of n plus 2 by 2 units. Third one is folded version, that is time inverted version of x of n. Fourth operation is inverted and right shifted by 2 units. Fifth operation is inverted and left shifted by 2 units. So it is very easy to graphically plot the signals. It is easy to shift the signals by graphically plotting these signals. Let us plot the original signal first and perform these operations on the signals. If we take the original signal, that is n versus x of n, varying on both the sides. So 1, 2, 3, 4, 5. These are the amplitudes defined at corresponding time instants. The first operation that has to be performed is x of n minus 2, or this is also called as delayed or right shifted by 2 units. What you have to do for performing x of n minus 2? To perform x of n minus 2, simply add the time index by 2 units. Simply add, because you have to right shift means you have to simply add the time index. When you add 2 to the time indices, what happens to this? You can see that this is x of n minus 2. So this minus 2 plus 2 is 0, 2 plus 2 is 4. If you observe the extreme limits, minus 2 plus 2 is 0, 2 plus 2 is 4. So original signal was varying from minus 2 to plus 2. Now that delayed version is going to vary from 0 to 4. So 0, 1, 2, 3 and 4. X of n minus 2 will be, so it is 1, 2, 3, 4 and 5. This is the right shifted version of this particular signal, shifted by 2 units. Now if you take the left shifted version, that is the second operation, that is x of n plus 2. N plus 2 is called as what? Advanced or left shifted by 2 units. Advanced or left shifted by 2 units. So original signal is this one, that is it is having 1, 2, 3, 4, 5 other amplitude values and is varying from -2 to +2. What you have to do to advance this signal? You have to just simply subtract 2 from the time indices. So if you observe the extreme indices, -2 minus 2 is 4, 2 minus 2 is 0. So the signal will vary from -4 to 0 for this left shifted version. So n versus x of n plus 2. So all will have the negative portion, -1, -2, -3 and -4. So it is having the signal is left shifted. So starting from -4, 1, 2, 3, 4, 5. So this is x of n plus 2. Now coming to the third operation, that is the folded version or inverted version, time inverted version. How can you plot the folded version or time inverted version? X of -n. Folded version is performed by shifting the positive side sample to the negative side and negative side samples to the positive side, keeping the 0th sample as it is. Keep the 0th sample as it is, shift the positive portion to the negative side, shift the negative portion to the positive side, and keep the 0th sample as it is to perform x of -n. So 0, 1, 2, plot this time indices now. What you are going to know, keep the 0th sample as it is, shift the positive sided sample to the negative side, that is 4 and 5 are present on the positive side, so shift to the negative side. So 4 and 5 will come over here, and on the negative side you have got 1 and 2 amplitude, so shift them to the positive side, 1 and 2, and the 0th sample is kept as it is. There is no change in the 0th sample. So if you represent this in the sequence representation, it is now 5, 4, 3, 1, 2 with the 0th sample located at 3. This is how we can represent the signal in the sequence representation. The graphical representation is converted into the sequence representation like this. So 5, 4, 3, 1, 2 is the time for this folded version of this particular signal. Of course, you can represent the same thing, you can represent for right shifted and advanced version also. X of n minus 2 is 1, 2, 3, 4, 5 with the 0th sample at 1. Similarly, x of n plus 2, the advanced version is 1, 2, 3, 4, 5 with the 0th sample located at 5. So like this you can, so I have performed the this operation. Now fourth operation is x of 2 minus n or x of minus n plus 2. Already have performed x of minus n. Now the thing is, next you have to perform x of 2 minus n. This is x of minus n. So what is this one? Fourth operation is x of 2 minus n. It is also defined as x of minus n plus 2. So it is inverted and right shifted by 2 units. Inverted and right shifted by 2. I already inverted the signal and you have got this x of minus n as 5, 4, 3, 1, 2, etc. Okay. So plot that particular inverted signal now. N versus x of minus n as 5, 4, 3, 1 and 2. When you are plotting, you clearly show the distinction in the amplitudes. For example, 4 is greater than 3, 1 is greater than 2, etc. So 0, 1, 2 on the positive side, 1, 2 on the positive side, -1, -1 on the negative side, 0 is the center sample. So 5, 4, 3, 1, 2 is there, that is x of -n. Inverted and right shifted by 2 units. Now what you have to do, you have to right shift it by 2 units. So what you have to do to right shift, just add the time index to this. So -2 plus 2 is 0, 2 plus 2 is 4. So signal is varying from 0 to 4. 0, 1, 2, 3, 4, etc. So this is signal is 5, 4, 3, 1, 2. This is x of 2 minus n or minus n plus 2. Finally, you have to perform the fifth operation that you have to perform is x of -2 minus n or x of minus n minus 2. What is this operation? This is folded and left shifted by, folded is otherwise called as inverted, folded and left shifted by 2. So already you have folded this, you have obtained the folded version of this, that is x of minus n you have obtained. Now once again you have to left shift it. Left shift it means it is, once again you have to subtract. Left shift means you have to subtract from this particular x of minus n, time indices. -2 minus 2 is 4, 2 minus 2 is 0. So the signal is ranging from -4 to 0. The signal is ranging from -4 to 0. So the amplitudes are 5, 4, 3, 1, 2. 5, 4, 3, 1, 2. Of course, you can represent them in this one also. You can represent sequence representation also. X of 2 minus 1 and x of minus n minus 2. X of minus 1 minus 2 is completely has become a anti-causal signal, negative side signal. X of 2 minus n has become a causal signal. Okay. So these are all about the important operations that can be performed on this particular discrete time signal. These are best examples where you can perform the discrete time signals. Now I suggest all of you to try this problem. You perform these operations. X of n is equal to, suppose the signal is 1, -1, 2, -2, 3. 0 is sample located at 2 here. So this is n is equal to 0, this is n is equal to 1, this is n is equal to 2. Negative side you have n is equal to -1, n is equal to -2. Perform these operations on these signals. X of n plus 1. Second one is x of n minus 1. Third operation is x of n minus n. Fourth operation is x of 1 minus n. Fifth operation is x of minus n minus 1. Try to perform these operations. I will give you as an exercise for this particular this one. Try by yourself. X of n plus 1, x of n minus 1, x of minus n, x of 1 minus n, x of minus 1 minus n. X of n plus 1, it is say it is advancing, time advancing by 1 unit. This is x of n minus 1 is time delayed by 1 unit. X of minus n is folded version. Fourth one is x of 1 minus n can also be interpreted as x of minus n plus 1. It is inverted and right shifted by 1 unit. Finally, this is x of minus n minus 1. It is inverted and or folded and left shifted by 1 unit. So be careful that you have negative amplitudes here. You should be very careful that you have negative amplitudes. Not all the amplitudes are not positive, but you have negative amplitudes here. So if you plot the original signal x of n, so the amplitudes are 0, 1, 2. Negative side you have -1, -2, etc. So 1, -1, 2, -2, and 3. This is the original signal you have plotted. Now you have to perform x of n plus 1, x of n minus 1, x of minus n, x of 1 minus n, and x of minus 1 minus n. Plot these signals. Okay, right. So the same operations can be extended to this discrete time signals also. The same operation can be extended to the discrete time signals also. infinite duration discrete time signal. For example, suppose you have got x of n is equal to u of n. You can perform, right, these operations on these signals. One is x of n minus 2. Second one is x of n plus 2. Third operation is x of minus n. Fourth operation is x of 2 minus n. Fifth operation is x of minus 2 minus n. The same operations, the same principles can be extended to the infinite duration signals also. So x of n is equal to u of n is given for you. That is a causal infinite duration signal. Unit step signal is given for you. First one is x of n minus 2. You have to plot x of n minus 2, which is a delayed version, which is delayed by 2 units or right shifted by 2 units. So the original signal is u of n here, having infinite number of samples of 1 like this. So the original signal is given for you is having the infinite number of samples 1, 1, 1, etc. So it is defined at 0, 1, 2, etc. Because the function representation for u of n is u of n is equal to 1 for n greater than or equal to 0, 0 for n less than 0. Now, if your first operation is x of n minus 2 delaying by 2 units, so just add this 0 plus 2 is 2, and of course there is no upper limit because upper limit is infinity, so it is ranges from 2 to infinity. So 0, 1, 2 starts from 2 here, so it has infinite set of amplitudes like this 1, 1, 1, etc. This is x of n minus 2. Similarly, x of n plus 2. N plus 2 is left shifted by 2 units. Subtract. 0 minus 2 is minus 2. So signal is starting from n is equal to minus 2. So 1, 1, 1, 1, etc. Ranges from this one. Be careful that you have to keep the dotted samples only on the side that is varying infinity. You should not keep the dotted samples varying on the finite variation. So this is xn versus x of n plus 2. Like this. And x of minus n. Minus n is nothing but it is time inverted by the signal is a folded version or time inverted version of the step signal. So u of n minus n looks like this. Okay, this is x of minus n. The fourth operation is x of 2 minus n is there. So 2 minus n is inverted and right shifted by 2 units. Inverted and right shifted by 2 units. Already have inverted it. Now you just right shifted by 2 units. X of 2 minus n. That is this is the dotted lines are represented on the negative side, meaning to say that it starts from n is equal to minus infinity, ends at n is equal to 2. And finally, x of minus n minus 2. So here the signal is still left shifted by 2 units. So if you plot this particular x of minus n minus 2 or minus 2 minus n, the signal gets still left shifted. X of already have plotted x of minus n, still left shifted by 2 units. That means the signal starts at n is equal to infinity and ranges up to minus 2. Like this. So these are the examples that you can perform these operations on the infinite duration signal also, causal signal also. Infinite duration causal signal. Right. So this is about the operations that you can perform on this particular infinite duration and finite duration. I have given you one problem as an exercise, that is 1 minus 1, 2 minus 2, 3, etc. Take it as an exercise and try with the operations in this side. Next classification of the signals is symmetric and anti-symmetric signals. Symmetric and anti-symmetric signals. So the other name given for symmetric signals is even signals. The other name given for anti-symmetric is odd signals. So a signal, discrete time signal, is said to be symmetric if x of minus n is equal to x of n. The best example is for this is cos omega n. Because cosine signal is always an even signal, even if you time invert it. That means, what is the physical significance of this? Functionally, mathematically, you are going to define f of minus t is equal to f of t. And here in signals and systems concept, you are going to define if the time inverted version of the signal is equal to the original signal, then it is a symmetric or even signals. So this is a condition for symmetric signals. If you take an anti-symmetric signals, x of minus n is equal to minus x of n. This is anti-symmetric or odd signal, symmetric or even signal. Best example for this is a sinusoidal signal, sin omega n. Because if you time inverted sinusoidal signal, you get the minus. Sin of minus theta is always equal to minus sin theta. Cos of minus theta is cos theta. Now, any signal is comprised of even and odd parts. Any signal is comprised of even and odd parts. X of n is always equal to xc of n plus xo of n, where this is the even component and xo of n is the odd component. Now, if you perform the time inverted version, x of minus n is equal to xc of minus n plus xo of minus n. That is equal to xc of minus n is xc of n because it is an even part. Xo of minus n is minus xo of n because it is an odd part. So x of minus n is equal to this one, xc of minus n minus xo of n. Call this as the first equation and this as the second equation. Now add up both the equations, you get 1 plus 2 implies, adding both the equations you get 2 times xc of n is equal to x of n plus x of minus n divided by 2. And 2 times xc of n is equal to x of n plus x of minus n. So xc of n becomes equal to x of n plus x of minus n whole divided by 2. This is the equation for the even part. How to extract the even and odd parts? So even part is equal to what? Original signal plus time inverted version divided by 2. Divided by 2 means, what is the physical significance? It is amplitude scaled version. It is amplitude scaled version. Okay, similarly, xo of n is equal to, xo of n is obtained by subtracting both the signals. That is 1 minus 2 implies 2 times xo of n is equal to x of n minus x of minus n. That is xo of n becomes equal to x of n minus x of minus n whole divided by 2. Xo of n is equal to x of n minus x of minus n whole divided by 2. That means the signal is subtracted. X of n minus the signal is subtracted from x of n, x of minus n is subtracted from x of n, and times this amplitude scaled by 2 units to get the odd part. This is the equations for even and odd parts. Now you have seen the different time shifting operations on the signals. So the basic broad classification of the operations are, if you take the operations or take all the operations on the signal, the first operation is amplitude scaling. The second operation is time scaling. The third operation is time shifting. Now just you have seen different time shifting operations on the signals. Fourth operation is addition of signals, addition and subtraction of signals. And the fifth operation is multiplication of signals. When you take up the first operation here, that is the amplitude scaling, a signal, discrete time signal x of n is said to be amplitude scaled if y of n is equal to some alpha times x of n. So here if alpha is greater than 1, it is called as gain. If alpha is less than 1, it is called as loss or attenuation. That means the signal gets scaled only in amplitude. Scaling means it is multiplying with the amplitudes. You are not disturbing the time here, you are disturbing only the amplitudes. For example, you have one x of n is equal to 1, 2, 3, 4 with a 0th sample located at 1. You can perform x of n is equal to 2 times x of n and some z of n is equal to 0.5 times x of n. When you take up the first case, that is y of n is equal to 2 times x of n, it is called as the amplified version. Amplified version. If you take the second one, it is called as the attenuated version. The first case is an amplified version, the second case is an attenuated version. So the original signal is 1, 2, 3, 4, you know, when you plot this one, 2 times gets scaled by 2 units. That means amplitude gets multiplied by 2. That is 2, 4, 6 and 8. 2, 4, 6 and 8 are the amplitudes located at 0, 1, 2, 3. Similarly, second one is 0.5 times x of n. X of n gets multiplied with 0.5. That is 0.5. 2 into 2 is becomes 1. 3 into 2 is 1.5. 4 into 2 is 2. 0.5, 1, 1.5 and 2. So the second one is called attenuated in amplitudes. This is about the amplitude scaling operation. Next operation that is there is time scaled version, time scaling. So if x of n is the original signal, then y of n is equal to x of an denotes the time scaled version of the signal. X of n is equal to an denotes the time scaled version of the signal. Okay, if a is greater than 1, it is that the signal gets compressed. On the other hand, if 0 less than a less than 1, the signal gets expanded. That means you are disturbing only the time of the signal but not the amplitude of the signal. Y of n is equal to x of an. You are disturbing only the time but not the amplitude. Example, best example here is y of n, x of n, suppose you take same signal, you take 1, 2, 3, 4, 5, let us say. You are going to perform x of 2n and you are going to perform x of n by 2 or x of 0.5n. How to perform x of 2n? Let us say y of n is equal to x of 2n. So what is y of 0? Y of 0 is x of 0, which is 1. 0 sample is 1. It is better to write down the sample values here. X of 0 is equal to 1, x of 1 is equal to 2, x of 2 is equal to 3, x of 4 is equal to, x of 3 is equal to 4 and x of 4 is equal to 5. So y of 0 is equal to 0, x of 0 is 1, y of 1 is equal to x of 2. What is x of 2 is 3 and y of 2 is equal to x of 4. X of 4 is 5 and y of 3 does not exist. Y of 3 is x of 6, which is 0. So only 3 sample values of the signals are existing. That is y of n is equal to x of 2n is what? 1, 3, 5. That's all. So the signal is getting compressed here. The signal is getting compressed here. When you take up the second operation, that is x of n by 2, the signal gets expanded here. You can observe the same thing. The signal gets expanded if you take this one. So meaning to say that zeros are introduced. Zeros if you perform this x of this one, the same way you can perform. You can take it in a size. With the same way if you perform the signal, you get the 1 0, 2 0, 3 0, 4 0, 5. These are the samples that the signal you can get. X of n by 2 becomes expanded, meaning to say that zeros gets appended in between the two things. You get zeros get appended in between the things. So the signal is getting expanded. So this is operation of time scaling. And just now we have discussed about different time shifting operations on the signals. That is right shifted delayed version, advanced version, inverted and right shifted version, inverted and left shifted version. All this I have seen. And coming to the fourth operation, that is addition and subtraction of the signals. Addition and subtraction of signals. So two signals, discrete time signals, are added if you are going to add their amplitudes, not the times. So add their amplitudes at the corresponding times to get the addition of two discrete time signals. Suppose you have two discrete time signals, x1 of n is equal to 1, 2, 3, 4, and x2 of n is equal to 5, 6, 7, 8. Let us say the arrow marks are defined like this. 1, 2, 3, 4, the arrow mark is 1, and this 5, 6, 7, 8, the arrow mark is this one. So how can you do this particular addition of this signal? So just best way is to plot this graphically and analyze these signals x of n. Okay, you have got this 1, 2, 3, and 4, and the second one is x2 of n. N versus x2 of n is like this. 8 is, so I have got 5, 6, 7, 8. Is 0, -1, -2, -3, 0, 1, 2, 3. Now we are adding these two signals. When you add these two signals, you can say that only the samples at 0 it gets amplitude is added up. Here at n is equal to 1, what happens? It is amplitude is 2, here it is 0. So 2 plus 0 is 2. Similarly, at 3 you have got 3 here, there is no 0th amplitude is here, is there? So 3 plus 0 is 3. So similarly at 3 you got 4, 4 plus 0 is 4. Like this you are going to define. So if you add up both the amplitudes, only at 0 here you get 2 plus 8, which is this 1 plus 8, which is 9. 1 plus 8 is 9. So y of n, if you call x1 of n plus x2 of n, y of n, if you take x1 of n plus x2 of n, you got here 5, 6, 7, 8. 5, 6, 7, 8, and here at n is equal to 0 you have got 9, and here you have got 2, 3, 4 as it is. The right side you have got 2, 3, 4. Left side you have 5, 6, 7. So you got left side you have 5, 6, 7. So 1 plus 8 has added up here. So 1 plus 8 is 9. So 0, 1, 2, 3. Next side you have -1, -3. So just you are adding their amplitudes here, that's all, but not the times. So add their amplitudes at the corresponding times. This is about the addition of the signals. Similarly, if you take the subtraction of the signals, take a simple example. Suppose x1 of n is defined as 1, 2, 3, 4, and x2 of n is defined as 2, 3, 4, 5. Obtain y of n is equal to x1 of n minus x2 of n. So the best way is once again to plot the signals and try to analyze them. N versus x1 of n is 1, 2, 3, and 4. And n versus x2 of n is 2, 3, 4, 5. So they are defined at 0, 1, 2, 3. Here also it is defined at 0, 1, 2, 3. Now just subtract the signals at the corresponding times. At n is equal to 0, you have got 1 minus 1. 1 minus 2 is -1. At n is equal to 1, you have got 2 minus 3. Once again it is -1. At n is equal to 2, you have got 3 minus 4. Once again it is -1. At n is equal to, you have got 4 minus 5. Once again it is -1. So -1, -1, -1, -1 will be the subtraction of the signals located at 0, 1, 2, 3. So y of n sequence representation will be -1, -1, -1, -1 like this. 0 sample position will not change here. Likewise, you need to subtract. So that is, you can define x1 of n minus x2 of n can be visualized as x1 of n plus minus of x2 of n. That means you are adding the Original signal x2 of n with the amplitude inversion version of x2 of n. What is the difference between x2 of n and x2 of minus n and minus x2 of n? x2 of minus n is the time inverted version, but minus x2 of n is the amplitude inverted version. It is the amplitude inverted version of x2 of n. So this is it is an equivalent operation. This both are equivalent operations. x1 of n minus x2 of n, subtraction is nothing but x1 of n plus minus x2 of minus n. Right. So in this lecture we have seen about the basic DSP system and the advantages and applications of the DSP systems, and our basic concepts of sampling, and we have started the classification of discrete time signals. We have seen the classifications of almost 3 classifications we have seen. And also these are because these are very important in our DSP systems, and also we have seen the operations on signals. Of course, in operations we have got different time shifting operations also with the examples for this section. So in our next lecture we will be seeing about the next concepts, that is the next classification of the signals. That is 2 more classifications are pending, that is periodic and aperiodic signals and energy and power signals. So let us take up the next the classification of the signals, then we go for the systems when we briefly study about the systems. So thank you so much.